Okay, good morning. So, statistics for data science, next lecture, and the topic today are random variables. And random variables really form the basis for the probabilistic models that you will encounter in statistics, machine learning, AI, and any kind of data science. So, the probability space models that we discussed last week on which random variables build, as we will see this week, are important as a theoretical foundation, but in an applied setting you will rarely see that a full probability space model and its associated random variable are conceptualized, but typically the formulation of probabilistic models starts with the definition of the random variables that are involved. So random variables is actually, or random variables are the basic units on which any statistical machine learning or AI models rest on. They are grounded in probability spaces, but this is definitely in applied settings usually not discussed. So another very foundational lecture today. So the material that we are covering today is really standard, so you find that everywhere. The stuff that I'm presenting is mainly inspired by the Wasserman and the de Groot and Scherwisch book, but really you find this everywhere, and it's good that you find it everywhere. So the plan then for today is to first discuss the theoretical basis of random variables, so the construction of random variables on the foundation of probability spaces, to give it a formal definition of a random variable, and then discuss some notation that is often associated with random variables. And once these kind of theoretical preliminaries are in place, then we discuss two very important concepts that are the key entities to define statistical machine learning or AI models, namely probability mass and probability density functions. And once we have that, we discuss cumulative distribution functions, which are useful specifically in statistics, in certain areas of statistics like confidence intervals, hypothesis testing. They are used a lot. They also have other applications, but that's where in this lecture they will feature then again a lot. So that's the plan. Good, then let's just get started. So construction, definition, and notation. And to construct a random variable and to give a definition, we start again with where we started last time. So we assume that we have a probability space with outcome space omega, sigma algebra, calligraphic A, and a probability measure as defined last week. And now we assume that we have a function which we call x, big X, which maps elements of the outcome space into another space, which we denote by this calligraphic X. So this X here. And we will always call this also the outcome space, as we will see later, the outcome space of the random variable as opposed to the elementary outcome space. But for the moment, we just say we have a function from omega to some other space, calligraphic X. And we assume that on this other space, calligraphic X, we can also define a sigma algebra, and this sigma algebra we call calligraphic S. Then we define for each set in the sigma algebra S, we define what we call the pre-image of S. And the pre-image we denote here by x to the or x superscript -1, I should say. And by the pre-image we mean those elementary outcomes in omega, so these small omega in omega, which are mapped by this function x onto elements in this set S, which is a subset of this calligraphic X. So we are basically considering those elementary outcomes in the original elementary outcome space that are mapped onto elements of a set S in the outcome space of this function. Now, if this pre-image, so if these omega and omega which are mapped onto elements in S are if this pre-image, which is a set of course because it's the omega, the elementary outcomes in omega, if this set is in the sigma algebra, and this holds for all S, so for all sets in the sigma algebra on calligraphic X, then we call the function H measurable. So what we're saying is we, in the outcome space, in the space that X maps elements of omega onto, we have sets. We look at the pre-images of these sets S, and if all of these pre-images, so this which are of course sets or subsets of omega, because it's the omega in big omega which are mapped onto elements in S. If all of these are in the sigma algebra R, the original sigma algebra, then we call the function X measurable. Why do we call it measurable? Why is it sensible to call it measurable? Because if these pre-images are elements of the sigma algebra, then they naturally get allocated a probability, because this probability measure of the original probability space, of course, allocates probabilities to all elements in the sigma algebra. And now if all these pre-images are in the sigma algebra, then automatically these subsets S of the outcome space of the function X, they get allocated a probability naturally, namely that probability that is associated with the pre-image. So this is written here. So we define a new probability measure, which we call Px, and Px maps elements of the sigma algebra on this outcome space X to the interval 0 to 1, because it will be a probability measure, and for each S, which is a subset of X, allocates to it a probability which we denote by Pxs, and this probability Pxs corresponds to the probability of the pre-image of S under the function X that is defined by the definition of the original probability measure on the probability space. And this already has been defined with the definition of this probability space, and it's just expressed here in two ways. So either we write it as the probability of the pre-image of S, or we write it as the probability of those omega and omega which are mapped by the function X onto elements in S. And in this construction X, so the function X is called a random variable, and the measure that we just defined as by means of essentially the original probability measure on the original probability space, this new measure is called the probability distribution, or the distribution of X. Now we have created in this way, or constructed, a new probability space, namely with this outcome space X, a sigma algebra which we assume to exist on this outcome space, and the probability measure that we just defined. And so we created a new probability space. And it's actually this probability space, if we make the additional assumption, for example, that X are the real numbers, and that the sigma algebra on this outcome space X is the Borel algebra, then it's this probability space of the real numbers, the Borel sigma algebra, and this distribution of X that takes center stage in probabilistic models. So before we go a little bit more into depth there, or mention some additional aspects of this. Here, yeah, a visual intuition of what I just described. So we have the original, or the basic probability space of omega, calligraphic A and P. And we have a function x that maps element of omega onto elements of another set x. And there we decide on a subset S of x, and then ask what are the elements of the original outcome space that are mapped onto elements of S by the function x. We call this the preimage, and the preimage, if this is actually part of the sigma algebra on omega, then we call this function measurable. And if it's measurable, we can easily assign a probability to the set S here in X, namely the probability that was associated with the pre-image of X, so this X minus S in here. So that's a visualization of what I just described. So based on this construction, we can actually, or we can give and have enough background to have an understanding of the definition of a random variable. So we define a random variable here as follows. So let's assume that we have a probability space omega Rp, and we have another space X, calligraphic X and calligraphic S, which we call measurable space. Measurable space just means that it's a set with an associated sigma algebra. That's what's called a measurable space. Then a random variable is a function from omega to calligraphic X, which of course maps elementary outcomes in omega onto its function values, x omega. And it is required, so a random variable, a function like this, it's called a random variable if it fulfills the measurability property. So that means, as we discussed already, that all pre-images, so these sets omega and omega, for which the elements are mapped onto elements in S, are part of the sigma algebra on the original probability space, and this holds for all sets in the sigma algebra calligraphic S. So the mathematical definition of a random variable is a function between a probability space and a measurable space. Essentially, this is always, sometimes maybe I have a remark on this, sometimes written differently, but it's a function from omega to x, and which fulfills the measurability property, or which is measurable. So which means that all pre-images of all sets in the sigma algebra S are in the original sigma algebra, because then we can assign a probability to each S in the sigma algebra calligraphic S. And this mathematical definition of a random variable has, of course, some interesting features. So although it's called a random variable, there's nothing random in it. It's a function, and functions are, these are the functions that you learn about in mathematics, or that we, if you follow the statistical methods course also that we discussed last week in statistical methods. Functions are deterministic, so there is nothing random in a function. And they are also not variables in the sense that you can substitute something for them or something. They are functions. Yeah? So random variables from a mathematical viewpoint are just functions. There's nothing random about them, and there's nothing variable about them. The question is, where does this stochasticity comes in, or where's the randomness modeled? So this is again the idea, I think I mentioned that last week already, that the omega the elementary outcomes in the elementary outcome space big omega are randomly selected according to the probability measure that is assigned to them. So you can view this as like a specific elementary outcome in the elementary outcome space is in a specific set, and this set has either high or low probability to be selected. And if you select an omega according to this probability and then map this omega onto x omega, this is then your realization of the random variable. So depending on the probability, underlying probability measure, you select also the values of the random variable. And yeah, as I mentioned already, the distributions, which are probability measures, of course, of the random variables, they are central in statistics, machine learning, and artificial intelligence. And as I already did all the time, because I have multiple x's here, and it's a little bit annoying to always say calligraphic x, this calligraphic x we call the outcome set of the random variable x, because these are the values that the random variable take on, and yeah, it's natural to call this the outcome set. Oops. Yeah. Before we see basically what now happens, and that we basically can focus on these induced probability spaces, which are created by defining a measurable space and then looking at probability distributions, so probability measures of random variables which are induced by this measurability property. Let's look at some notational conventions. Let's assume that we have a probability space omega Rp, and this induced or P, and this induced probability space X as Px. And of course, these are the probability spaces relating to some measurable function or a random variable x. Then the following notations are often used. So if you you have these usually you have these curly brackets, and then you can, for example, write x is an element of S, or x equals x. So this is very prominent notation, of course, so that a random variable assumes a given value, or that x is smaller than a given value, small x. What these things refer to, these are events, and these refer to the pre-images. So with, for example, this event here, x equals x, what is meant are the omega in the original omega space for in the original probability space, for which x omega equals the value small x. Yeah. So one in terms of these events that one defines of random variables, one should always relate these events back to the events in the underlying probability space and their in their original sigma algebra. So this is then what these things mean. So if you have here a probability distribution, which is denoted here by px, and you think about the event that, or you refer to the event that x is an S, which you can also write without these curly brackets. What this refers to is the underlying probability, so that's why the x is missing here, of the pre-image of this event, which are the small omega and omega, for which x omega is mapped onto or an element in S. So if you see like a random variable takes on a value smaller than x, what this is supposed to mean is, or you talk about the probability under the probability distribution px, that a random variable takes on a value equal or smaller than x. What this means is that you talk about the probability of the pre-image of the, this event, which is defined as the underlying probability. And what happens in addition is that often, if you talk about probability distributions, the subscript x is omitted, which is somewhat dangerous, because then of course there is the danger of confusing which probability measure is actually talked about here. Here this can, of course, it's not really clear that this refers to the distribution. It could also be this underlying probability measure. So if you work mathematically very carefully, you would use this subscript notation. However, as I will show you in a second, there is a specific case, namely when the random variable is the identity function, where this in a way does not really matter, and then of course it's a little bit annoying to always have the subscript x here when you see that you're talking about the distribution of a random variable x. So this is why in real life, and also in much of the notation that will follow, I will omit this subscript, because then you always see that you're talking about a random variable, and then you have this additional subscript x, which does not really add that much information if everyone agrees that what these things mean are actually the probabilities of the underlying probability space, which often is not made explicit, and that's maybe a little bit hard to get used to. So, good. Now this is the mathematical construction of random variables, and this is really helpful if you do mathematical work in probability theory, if you define concepts, and if you specifically, if you try to link continuous and discrete random variables under one unifying framework, and and most of the relations between probability theory and measure theory are spelled out exactly like this. And then actually in math, and that's something I didn't mention yet, often you might not even talk about random variables, but you just talk about measurable mappings or measurable functions, which are in the mathematical world of probability theory are equivalent to the notion of random variables. However, of course, in real life, if you think about, I don't know, what you learned in, I don't know if any one of you had some psychology undergrad statistics or something. Random variables are not constructed this way, but it's more like, we model something by a random variable, if this is mentioned at all, and this random variable has this distribution. And of course, that's all fine. So the question is, how can one now interlink these notions of underlying probability spaces, random variables, and then what we will focus on from now on which what you will definitely already have seen, namely the notions of probability mass functions and probability density functions. How can one interlink them? And this is explained here. So clearly, the distributions of random variables are central in probability and statistics, so we always talk about the distribution of a certain random variable, and later when we go to the statistics part of this course, we will assume, for example, that there are 10 random variables and they are Gaussian distributed or something like that. These distributions we will then specify in terms of probability mass functions and probability density functions, which I guess you also know roughly what they are, so we will look at them in more detail later, but you roughly know what they are already. But the question is then, what's with the probability spaces and what's with the probability measures if we don't talk about them anymore? Well, one way to think about this is, if you haven't seen how they can be useful in pure mathematics, is that you can always, when you talk about the distribution of a random variable, you can always basically construct the underlying probability space very easily by using the identity mapping. So this shows some equivalences here. So assume that P is a probability measure on the Borel sigma algebra, and that you define a probability space omega F, it should be an A, but that's fine. F is the sigma algebra here, P as the set of real numbers, the Borel sigma algebra, and P. And now you assume a mapping from omega, which are the real numbers, to the real numbers, and you map each omega onto itself, so you use the identity function. Then, of course, the distribution of x is just the original probability measure, because nothing changes. The function doesn't do anything, so it we will talk more about what happens when you apply functions to random variables or things that have a probability measure associated with them. But I think it's intuitively clear, if the function does nothing, then of course the probabilities of these events and also these outcomes that are mapped by x onto themselves does not change. So this then means that any probability space that you define, you can understand as the distribution of a random variable. The other way around, you can understand every distribution of a random variable, or let's say the other way around, for every distribution of a random variable, you can very easily define the underlying probability space by assuming that the random variable is the identity function, and then you specify its distribution by means of, for example, a probability density function. So you specify a probability measure px by means of probability density function or probability mass function. Then if you ask yourself what's the underlying probability space, the easiest model to choose is that you assume that the random variable is the identity function, and then your underlying probability space is just your probability space of the random variable. So it's always there. Often in applied probability theory, there's basically no talk about the underlying probability space, because it's not required, because it doesn't help to clarify certain aspects. In other situations, for example, if you model something by, we will see that later with the 2 dice example, if you model a random experiment by a probability space and then you do something with the realized outcomes, then it's very helpful. Or if you're trying to, for example, unify notions of certain aspects of continuous or and discrete random variables under one framework, then it's useful. It's always there, but we can safely but still mathematically grounded focus on distributions, so the probability measures of random variables in the remainder of the course. And if you, for each probability measure for each of a random variable, so for each distribution, you want to ask what's the underlying probability space, I can always tell you, well, just assume that the random variable is the identity function, and then you already have your underlying probability space. Good. So the focus in the remainder will be then on distributions. And distributions, again, are the probability measures of random variables, which are mathematically defined. Let's go back to the distribution, where we have the distribution. Are defined as the probability measures of random variables, which are mathematically grounded in an underlying probability measure, but we can also talk about and defining the this distribution, the probability measure, not by means of its underlying probability space, but by other means, namely by probability mass and density functions. And then we can always construct an underlying probability measure based on what I just said, based on the assumption that the random variable is the identity function. And this is what we will do in the remainder of today's session. Good. So the next parts, specifically with probability mass functions and probability density functions, I assume this will be largely review of what you have seen before, and maybe cumulative distributions functions are a little bit special. Good. I would suggest that we have a break before we start probability mass and probability density functions. Are there questions right now about random variables and this construction? Okay, then let's continue. I think what I tried to explain there in the end, before the break, was actually the notion of a probability function, and the question of distribution functions. That's a little bit weird, and the most important concepts are the things that we have on the slide. This is why I was confused by the question, because we will talk about probability mass function, we will talk about probability density functions, and we will talk about cumulative distribution functions. And distributions functions per se are not really something. They are called cumulative distribution functions. There is the notion of a probability function defined on these elementary outcome spaces, but that's something that we don't talk about. So let's focus now on what is actually relevant, namely probability mass functions, probability density functions, and cumulative distribution functions. And the reason why they are relevant, and based on what we just seen, there are essentially two ways to define the distributions of random variables, so the probability measures that are associated with random variables. One way is by construction of an underlying probability space, the definition of the functional form of the random variable, and then an assessment of the probabilities associated with the inverse, with the pre-images that are of interest. The other way, and this is what I explained with the last slide before the break, is to directly define these probability measures associated with random variables, then always having the possibility to construct the underlying probability space by assuming that the random variable is the identity function, and defining these probability distributions then by means of these entities that we have here: probability mass functions, probability density functions, and cumulative distributions functions. So these are and it's this latter approach that is most commonly chosen in statistical modeling, machine learning, and AI. So let's focus on what these things are. And here, even if the stuff in the first hour was maybe a little bit new to you, depending on what your background is, if you're from mathematics, that was not new to you. If you're not from mathematics, it might have been new to you. What's happening next, this is actually what I think everybody who has had a course on probability theory or statistics has heard about. So, probability mass functions. We use this definition and also then make clear that probability mass functions are always associated with discrete random variables. So let or we use this definition: a random variable x is discrete if it takes on countably many values in x, and the most common case is that it actually, or maybe not the most common, but the easiest to think about case is that it's actually finite many values, x1, x2 up to xn. We allow here for the countably many values, and for a discrete random variable, the probability mass function of x is defined as a function from the outcome space to the interval 0, 1 to each outcome value x. Px is associated, and that's the probability that x takes on the value x. And here already can think about whether this is now referring to the distribution or the underlying probability measure. It does not really matter, because as I explained, you can always use the identity function. Countable I explain below, and a probability mass function is non-negative, so that means that that px is larger or equal to 0 for all x in the outcome space, and it's normalized because it's a probability, so all the probabilities of the outcomes of the random variable sum to 1. And this is just by definition that the a probability mass function is defined as the probability that x takes on the value x. Note that I write probabilities with a big P, and probability mass function and probability density function will be denoted with a small p. And then I always have examples here for probability mass and density functions. So a very basic example for a probability mass function is a random variable with the outcome set 0, 1. And associated probability mass function given here, where px is defined as mu, which is a value between 0 and 1 to the power of x times 1 minus mu to the power of 1 minus x. And if a random variable has this probability mass function, then x is said to be distributed according to a Bernoulli distribution with this parameter mu, and we write for that, and this is some notation that we will see throughout the course, x is distributed according to a Bernoulli distribution with parameter mu, and the probability mass function of a Bernoulli random variable we abbreviate by this notation here. There we make the argument explicit and then have a semicolon and then have the parameter, and this is just a short notation for this expression here. Yeah, so this is actually notation that we will use for all probability mass and density functions. So we say a random variable is distributed according to a specific distribution, and if we refer to the probability density function or probability mass function and mean this the specific functional form of this, then we include the x as an argument to differentiate the idea of a distribution from the associated probability mass function. That's if you start computing and calculating and doing proofs with random variables, it's helpful to be a little bit careful with the notation there. Clearly you all have seen Bernoulli random variables. They can be used to model single biased coin flips or anything that has binary outcomes. Be aware that the outcome of a Bernoulli random variables are zeros and ones and not A and B or I don't know, kangaroo and frog, because they have this probability mass function, and this works if x can only take on the value 0 and 1. Because then, for example, if you're talking about x taking on the value 1, then you get mu 1 times 1 minus 1, so you get to the power of 0, which is 1, and you get mu. So mu is the probability for x to take on the value 1. There are things like categorical distributions which are not defined as such, but Bernoulli random variables are defined this way. Here's a picture of different Bernoulli distributions, and more specifically, so this is an example for Bernoulli distribution, but what is shown here are the probability mass functions. For example, Bernoulli probability mass function with parameter 0.3. So you see that x gets allocated x equals 1 gets allocated a value of 0.3, and 0 gets allocated a value of 0.7, 4.5, 0.5, and so always the mu corresponds to the probability mass that is associated with the outcome value 1. There are, of course, many more discrete random variables. I include the binomial random variable here and some picture of that, and the discrete uniform random variable. It's always the same kind of definition and same kind of notation. Have a look at them. We don't need to discuss them. We will actually see a couple of examples later on in the exercise session. They are essentially in here for reference, so at one point we will need these distributions, so we have them already in place, and they just serve as examples. Of course, there are many discrete random variables, and this is of course not an exhaustive coverage. That was already what I wanted to say about probability mass functions. We will see probability mass functions again next week when we talk about, and we will see them often, but next week explicitly when we talk about joint distributions. Maybe a little bit more common, at least in classical statistics, are probability density functions, which model continuous outcome spaces. Maybe one thing I should emphasize while we're looking at these examples, you see here that I used this stem plot instead of like putting a line or something like that, and this is motivated, of course, by the fact that these random variables only take on a finite number of values and don't take on values in between these values. Yeah. So, if, for example, here a uniform distribution takes on these values 1 to 10, for example, if it's a uniform discrete distribution with parameter 10, and it doesn't take on any other values, so it doesn't assign probability mass to any other values, like for example 4.5 or something. So this is why these stem plot representations of discrete distributions make a lot of sense. They even make a little more sense than these histogram, or not histogram, the bar-like representations, which then always cover some extended aspect on the x-axis, which is not really what's happening in a probability mass function. Now, of course, these discrete outcomes, if you think about, it depends on how you think about it, but most, let's say in neuroimaging, for example, the data are or reaction time data or whatever you're thinking about is modeled by the real numbers, and then of course these discrete random variables with these discrete outcomes don't apply, and also the calculations get a little bit easier if you use continuous outcome spaces. However, that really depends on the application, so I wouldn't on the application domain. So in my life, probability density functions play a bigger role, and classical frequentist statistics, specifically with this linear models that have some Gaussian assumption in it, they really are based more on continuous random variables and probability density functions, but I guess there's also a lot of probability mass function discrete random variable models out there. For me, probability density functions are a little bit more important, and for classical statistics in the linear model scenario definitely as well. So what are probability density functions? And what random variables are they associated with? So that's the definition that we use here. So a random variable x is continuous if there exists a function p from the real numbers to the non-negative real numbers, where each real value x gets allocated a function value px, such that the px are non-negative, which is already implied by this range definition here. Importantly, the integral over the real numbers of such a function is 1. This is also referred to as that probability density functions are normalized, and the probability that x takes on a value between two real numbers, a smaller or equal than b, is given by the integral of the probability density function over this interval, which is bounded by lower bounded and by a and upper bounded by b. So probability density functions are functions. These are just functions, but they have specific properties, and the most important, and these properties are that they are non-negative, and they integrate to 1 over the entire real line. So they was also referred to as being normalized. What's sometimes confusing people when they see PDFs, that they can take on values larger than 1, but that's not too confusing. That's just because they refer to a density and not to a probability mass. the probability for a continuous random variable to take on any specific value a is 0, because there are really many real numbers. That's one way to look at it. And formally, based on this definition, of course, the probability for x being a is the integral from a to a, which is, of course, zeros. The important thing to realize about probability density function is that you obtain probabilities from them by means of integration. So they are a density, and a probability is a mass, and you only get to a probability from a probability density function by essentially multiplying it with the volume that you want to assign a probability to. So they are, and this is also reflected in the name, of course, they are completely analogous to density in physics. So if you consider probability equivalent to mass, then if you think about the mass of an object, if this object has 0 volume, then of course it also has 0 mass, and the density is just the mass associated with a unit volume. So if you want to evaluate the mass of a specific volume of an object of a specific type or a specific substance, then you need to multiply the volume of this object with the density, and then you get the probability mass. And this is this is the way the probability density functions work. Of course, this is all based on this problem that the real numbers are uncountable, and that you still want to use them to model stochastic experiments or stochastic phenomena. And you can do that by assigning probabilities to integrals of probability density functions. That's the crucial thing here. And then, of course, the most famous probability density function is the probability density function of a Gaussian random variable. So if you have a random variable with outcome set corresponding to the real numbers, and the probability density function given by 1 over the square root of 2 pi sigma square times the exponential of minus 1/2 sigma 1 over 2 sigma square times x minus mu square, then you call this a Gaussian random variable, and you say that x is distributed according to a Gaussian distribution with parameters mu and sigma square. We write for that x is distributed according to n mu sigma square, and the PDF we abbreviate again with this extra x in there. So that's this thing here is just a short notation for this function. Again, it's a function, a probability density function. One or actually, because mu and sigma square are parameters that you can vary, this is actually defines infinitely many Gaussian distributions. There's a special Gaussian distribution, namely that with parameter mu being 0 and variance parameter sigma square being 1. This is called the standard normal distribution, and sometimes also referred as a z variable, actually often, not sometimes. And of course, you have seen the probability density function of Gaussian variables before, and you know that the parameter mu specifies the location of highest probability density, and the parameter sigma square specifies the width of the distribution. So here examples. Here we have the standard normal distribution with mu parameter 0 and variance parameter or sigma square parameter, because we don't know what expectations variances are. So for today they are called mu and sigma square parameters 1. So that looks like that. If you increase the sigma square parameter, you get a wider width. You shift this around by setting the mu parameter differently. That's what you see here. And importantly, what you can read off of them are not probabilities. And that's very different from what we've seen here for probability mass functions. Here you can read off that the probability for the random variable x to take on the value 2 is 0.5. Here you can only, so you can read off all the time that the probability for the random variable x to take on the value, for example, 1 here is 0, because that's the case for all continuous random variables. So this is what you can always read off. But if you want to talk about non-zero probabilities, you need to talk about the probabilities associated with intervals. So for example, the probability associated with the random variable taking values here between 0 and 5, and this probability derives or corresponds to the integral of this probability density function over this interval from 0 to 5 as defined here. Yeah. So this is how probability density functions work. And then there are of course many probability density functions. So I include here the gamma density function for gamma random variables, which are related to what we will also see later on chi-square variables, where we will not see exponential distributed random variables. And then there are another distribution that we can talk about, and we will see when we talk about Bayesian inference. I think that's the first time they come really around. Are better probability density functions. And again, there are very many probability density functions and associated random variables, and this is just a collection that we can use for reference. And again, we will see some of examples later on in the Übung. There's also a uniform continuous random variable, so make sure that you are clear about the difference between a uniform discrete random variable and a uniform continuous random variable. Good. So these are the basic concepts of probability mass and probability density functions. Again, we will see them next week again in a little bit more interesting scenario when we look at bivariate or multivariate distributions. The crucial thing at this point are that you're clear the probability mass functions are associated with discrete random variables, and that the value of a probability mass function corresponds to the probability of the random variable to take on a specific value, whereas probability density functions are associated with continuous random variables. They are like probability mass functions, they are functions, but they have specific properties, namely that they are non-negative. They integrate to 1 over the entire real line, and they relate to the probability that the random variable takes on a value in a given interval by means of integrals. So these are the things that at this point you should be clear about for probability mass and density functions. Now for the remainder of today's session, I would like to talk about cumulative distribution functions. And yeah, we take a little bit of time. So although cumulative distributions functions are, let's say, not as essential as probability mass and density functions, they are a little bit more subtle. So it makes sense in terms of understanding to spend a little bit time on it. I think probability mass and density functions, once one has seen a lot of probabilistic models, one is quite used to, and that's all fine. But then at one point one always needs also to look into cumulative distribution functions, and this is then a little bit more of a hassle. So I spent a little bit more time on those now. So first, we use this definition here. The cumulative distribution function of a random variable x is defined as big P, so that's in distinction to probability mass and density functions. And it's a function from the real numbers, regardless of whether we are dealing with a discrete or continuous random variable. So this is not specified here. to the interval 0, 1, and each x, each real number, gets allocated CDF value p of x, which is defined as the probability that the random variable x takes on values smaller or equal to x. So the first important thing is to appreciate that CDFs are defined for both discrete and continuous random variables, which essentially is the same as the next remark here, that p of x is defined for every real number, even if this real number is not in the outcome space of x, which we will see examples for. What cumulative distribution functions are useful for is, for example, evaluating interval probabilities. The thing is, one can, and this is what you will see in different texts differently, one can define the distributions of random variables in two ways, either by means of defining the CDF and then following or deducing their associated probability density or probability mass function, or one can define them in terms of PDFs and PMFs and then evaluate the associated CDFs. And we use the latter approach because it's just more common, and yeah, at least to me it also feels less complex, but it's definitely much more common these days. But of course CDFs can sometimes be useful, and for example, if you as we will see later on, if you are dealing with things like hypothesis testing or confidence intervals, you need to you have already if you did some undergrad statistics, and you will again deal with CDFs. So we view CDFs as a consequence or something following from the definition of a random variable by means of its PDF and PMF. One could do it the other way around, but we do it this way. So these are some properties of cumulative distribution functions, which can, the other way around, could also be used to define the notion of a CDF and then follow from its PDF and PMF properties, but again we do it the other way around. If we have a random variable and we let p denote its cumulative distribution function, then p has the following properties. So p is non-decreasing, that is, if x1 is smaller than x2, then the CDF value that is associated with x1 is equal to or smaller than the CDF value associated with x2. The limit of a CDF if x goes to minus infinity is 0, and if x goes to infinity is 1. And then the most subtle thing, maybe that's even the most subtle thing in the entire lecture, is that CDFs are right continuous, meaning that the value px corresponds to the right continuous or the right limit, or the what's it called? Yeah, the right limit of x. Namely, if you go 2x from the right side, so you go from y to x via y's that are larger than x, then this limit corresponds to the value px. We will spend a little bit more time on that, and actually in the exercise session later see that you can also do it differently, but that's how it's done. So as I already said, the listed properties can also be used to define the very notion of CDFs. This right continuity is intuitively the same as saying that no CDF jumps occur when limit points are approached from the right. If you have the CDF of a discrete random variable, there will be jumps and there will be instances of non-continuity, but they will only happen if you go from left to right and not if you go from right to left, based on the definition as the probability for the random variable to take on values equal to or smaller than x. So here are some proofs for 1 and 3. 2 I leave out, and of course you can also read up the proofs in the Groot book. So this is from the Groot book. So why this non-decreasing nature? Well, we first recall that for events in the elementary outcome space, it holds that if A is a subset of B, then the probability associated with A is equal to or smaller than the probability associated with B. Then if x1 is smaller than x2, the event that x takes on a value equal to or larger equal to or smaller than x1, of course corresponds to the set of the omegas in the elementary outcome space, which are mapped onto values that are smaller or equal to x1, which are of course a subset of those which are mapped onto elements that are smaller or equal to x2, because x2 is assumed to be larger than x1. And hence we have, in terms of these two events, we have this subset nature here, and this is why then immediately it follows from this property that these probabilities, there are some brackets missing, that these probabilities are related by this inequality, and these probabilities just correspond to the CDF values. We omit this with the limits. I think that's also very intuitive. What is really a little bit more subtle, and something that I've been struggling with in preparation, and I'm still struggling with, also because it's not really that important from an applied perspective. So in real life I never really have to deal with that, because I'm also not dealing with discrete distributions much. Is the question of this right continuity. And here what I'm defining is this value of px plus as the limit for approaching x via y's that are larger than x. And now we assume that we have a sequence of y1, y2 and so on, such that the limit for n going to infinity of yn is x. Then the event that x is the random variable is smaller or equal to x corresponds to the infinite intersection of of the events that x is smaller than yn. So of course yn is first, assume that yn is first very much larger, and then you make it smaller and smaller and smaller, so that you at one point are approaching the small x from the right. And then if you think about the CDF value as the probability of the event that the random variable takes on a value smaller or equal to x, this then of course, if these two are equal, corresponds to the probability of this infinite intersection. And then a miracle occurs, namely that this is actually identical to the limit of the probability of the events that x are smaller or equal to yn. And this was defined as this px plus. So of course the magic here is in this equality, which again is quite subtle, and one needs to dive deeper into the math to justify that. So the fact, and this is also maybe what we see again this afternoon, the fact with the right and left continuity of cumulative distribution functions, that's actually quite deep, and yeah, of more, at least for me, of limited applied value, but also so it doesn't really justify at least for me, to go too deep into that. Now we basically what we have done so far, just to recapitulate and don't get lost in proofs here. So we've defined the CDF as a function that allocates to each real value the probability that a random variable takes on a value equal to or smaller than x. And we have seen that from this definition there follow at least these three properties: that it's non-decreasing, that it approaches 0 if you go to minus infinity and 1 if you go to plus infinity, and that it's right continuous. But we haven't really talked about how they look like, and now for continuous or discrete random variables, and this is what we want to do now. So if we consider discrete random variables and we assume that the probability for x to take on values between any two real numbers is 0, then the cumulative distribution function, here included an x, which we can delete, is constant and horizontal in this open interval, because nothing happens. At every point where this discrete random variable, we're only talking about discrete random variable, has a probability larger than 0, the CDF jumps, and it jumps by the amount of the probability that x takes on this value small x, which is the same as what the PMF, sorry, the probability mass function does, because that's defined as this. And in general, a discrete random variable with outcome space natural numbers including 0 has the CDF that corresponds to the sum of all probabilities of taking on these discrete values k, where the sum goes up to the floor of x, which is the nearest integer, the nearest smallest integer. The point of this is, and this is actually more important maybe than the technical definition here, because what it actually would mean also a definition of the floor function, which I think is relative intuitive. So you just perform the floor operation, but to write down what the floor operation is, this is again a little bit more annoying. The point of this is that the CDF of a discrete random variable is defined for all real numbers, but only changes at locations where the random variable actually takes on values with non-zero probability. Yeah? And this is shown here, although it's a little bit cut off. It actually might be even nicer to see here. So it's a little bit cut off here, unfortunately. Sorry, that was not very good. But it's also seen here. So we have the probability mass function of a Bernoulli distribution in the background, and what we're looking here at is the CDF. And if you first focus here, please, of course a Bernoulli random variable does not take on the values 2 or 3, but of course we can, for each small value x, talk about the probability that the Bernoulli random variable takes on a value smaller to or equal than 2 or 3. And of course the probability that it takes on a value smaller than 2 is 1, because it only takes on the values 0 and 1 in the first place. So we can assign a CDF value to each real value, even if our random variable is discrete. And in terms of the discontinuities and the jumps that occur here, so that's what this says: at every point where the probability for x taking on the value x is larger than 0, the CDF jumps. This is what we see here. So if we go here and here, I think it's a little bit hard to see that there's also a blue line. You should imagine a blue line. I think it's because I set the y limits to 0 here and it cuts off the blue line a little bit. There's also a blue line here, but then at 0, and it's always at 0, and then it jumps by the probability for the Bernoulli random variable to take on the value 0, and that's if it's if the parameter is 0.3. This probability is of course 0.7, because that's the probability for taking on the value 1. So then the probability here for taking on values smaller or equal to 1 is of course 0.7, because the probability for it to take on the value 0 is 0.7, and then again it jumps at 1, because then the probability for it to take on values smaller or equal to something larger than 1 is 1. And this shows CDFs for other settings of the parameter. Same for binomial distributions. Again, you see these jumps. So that was basically the CDF story for discrete random variables. The important thing there is really to realize that the CDF is defined for all real numbers, although discrete random variables only take on usually either a finite subset of the real numbers or a countable subset of the real numbers if you think about Poisson distributions. Now the story is a little bit maybe less complex, or feels a little bit more natural, I think, at least to me, if you're talking about continuous random variables. So if you have a continuous random variable with PDF P and associated CDF big P, then it turns out that the value of the CDF P of x corresponds to the interval of the PDF small p from -infinity up to x. And this is very natural because that's how probability density functions allocate probabilities. And we're talking about the event of the random variable to take on a value smaller or equal to x, and of course you get this by integration, and if you're talking just about smaller than x, you need of course to start the integration at -infinity and stop at x, so you get to this integral. However, this formula here, or this little equation, if you are familiar with indefinite integrals from calculus, is of course basically a representation of the relationship between antiderivatives and derivatives. So from this it follows immediately that the PDF is actually the derivative of the CDF. Here's a little proof, although it's more saying you know this from calculus. So we first note that the probability for x taking on a value x is 0, so the CDF doesn't have jumps, it's continuous, and the antiderivative nature of the CDF with respect to the PDFs follows from how you get probabilities based on PDFs, and then the derivative nature follows by the fundamental theorem of calculus. If you're not happy with that, have a look in my calculus script for statistical models. That's where actually I provide or I discuss a proof that this is actually the case. So the bottom line here is that the CDF is the antiderivative of the PDF Stammfunktion, and the PDF is the derivative of the CDF. If you study this from a mathematical viewpoint, actually you know this identity under the label Radon-Nikodym theorem, which is relates different measures by means of the Radon-Nikodym derivative. But it's if you get back to the case of PDFs and CDFs, that's actually this relationship here. So let's have a look at how the CDF of a famous PDF is looking. So the PDF, let's assume we have a Gaussian distribution. So we have a PDF of x that is given by the Gaussian PDF that we've seen already. Now, if we want to evaluate the CDF, we just learned that we need to form the integral from -infinity to x of this PDF, and this is what we write here. So we form the integral, we can take this constant factor out, and then we have this integral. And normally you would now assume that there is that you can form the antiderivative of this, and then you can use the fundamental theorem of calculus, and you get a nice formula for the CDF. However, this is not the case for the Gaussian. So this actually can only be evaluated numerically. Sometimes you see this also expressed in terms of the error, so-called error function, which then is something that needs to be evaluated numerically. So interesting fun fact, the most important PDF in statistics, the CDF doesn't have a closed form but needs to be numerically approximated. Um, Yeah, so one needs to be careful that one doesn't get confused there, at least that's for me. So the probability density function takes on some values that are quite hard to interpret. So like I said, they can be larger or than 1, or they can be very small and so on. However, the values of CDFs, they are always really easy to interpret from a probabilistic perspective. So for example, if you have a Gaussian with mu parameter 1 and variance parameter 1, and you look at the CDF value at 2, that's then referring to the probability that this Gaussian random variable takes on a value equal to or smaller than 2, and that's 0.84, so associated with high probability, or more than 80% probability if you want to use a very colloquial language. In statistics, you will also find the notation of small phi and big phi for the PDFs and the CDF of a standard normal. So this is something that you might come across often, and we will also come across. So these are the CDFs of various Gaussian functions. So what you can readily appreciate here is the fact that they go to 0 for minus, for going to minus infinity, to 1 for going to plus infinity. And then you can, and this is how you should read that, at each point of x you can read off the probability that a Gaussian random variable with these parameters takes on values smaller than the given value that you choose. So for example, let's do something more or less meaningful. So the probability that a Gaussian random variable with expectation or mu parameter minus 2.5 takes on a value smaller than 0 is above 0.75. So it's quite large compared to a Gaussian that is centered on 0. There the probability to take on a value smaller than 0, of course, because the Gaussian is symmetric, is exactly 0.5. And they can, of course, look quite different for different distributions. This shows CDFs associated with better distributions that we visualized earlier. Good. Now for the last few minutes, the notion of inverse cumulative distribution functions, or quantile functions. So what we are doing right now is that we, with a CDF, we think about a value that the random variable either can take on if it's a continuous random variable, or some real value for a discrete random variable, and we want to know the probability that the random variable takes on a value smaller or equal to this value. Now that's interesting, but sometimes we want to we have a probability. So for example, if you are in hypothesis testing, we have a probability that we want to ensure. For example, we want to make sure that the probability for a random variable to take on values is smaller or equal to 0.05. And then the question is, what's the associated value in the outcome space at which this probability for the random variable to take on values larger than this value in the outcome space is fulfilled. So we, instead of going from values in the outcome space to the probabilities, we go from the probabilities to values in the outcome space. And this is of course the inverse operation here. And for that, we define first the inverse cumulative distribution function, which only exists for continuous random variables, and we define as p superscript -1, which now goes from probabilities 0 to 1 to the real numbers, and associated with each probability q a value p superscript -1 q, which is that value in the real numbers, so in the outcome space of this continuous random variable, for which the CDF takes on the value q, and this is called the inverse cumulative distribution function of x. And this is actually, if you ever did t-tests or things like this per hand, you used all of this to look up critical values, but it maybe wasn't that formalized. You only looked into a table and then you looked up critical values. Now p minus 1 is the inverse function of p, so if you apply, that's again x too many here, if you apply p minus 1 to px, you again get x. By definition, if the CDF of x equals q, then of course this is the same as saying that the probability of the random variable x to take on values smaller than x is q, which means that for every q in the interval 0, 1, p minus 1 q is the value of the random variable, such that the probability of x to be smaller or equal to x equals q. And for me, the easiest is always to make this clear with numerical examples. So for example, if you have a standard normal distributed random variable z, and you denote its CDF by big phi, and then you plug in a probability into phi minus 1, for example, the probability 0.975, you get back the value 1.96, and this is the value such that the probability for the random variable z to take on values smaller. This is the value such that the probability for x to take on values smaller or equal to 1.96 is 0.975. So in principle this is all easy, but then spelling it out sometimes is a little bit tricky. So let's go to the can go here. So we are talking about actually this distribution, and what we just saw is that if we are at roughly 2, then so 1.96, the probability for this random variable to take on values smaller than 1.96 is 0.9725. The other way around, if we ask what is the probability for what is the value at which the random variable takes what is the value in the outcome space of the random variable such that the probability for the random variable to take on values smaller than this value is 0.975. The answer is, well, we look at the ICDF, the inverse CDF, and the answer is 1.96. So here are visualizations of the relationship between the CDF and the inverse CDF. So there are 3 Gaussians here with different parameters, and on the left you see the CDF, which of course depends on the parameters. So maybe let's focus on the blue one, which is the standard normal. Now this shows the CDF, so we go from a value in the outcome space of the random variable to the probability that the random variable takes on a value smaller than that, which for example again for the 0 is 0.5. The inverse CDF goes, of course, the other way around. So here on the x-axis we have probabilities, and we get, if we for example look at 0.5, we get the value corresponding to the outcome value of the random variable at which the probability for the random variable to take on values smaller than this value is 0.5, and that's 0. And if we go to, for example, 0.975 or roughly towards 1 here, we get values close to 2. And that's the easy case for inverse CDFs. The more complex case is if we are talking about not continuous random variables, but random variables in general. To invert the CDF here, or let's say it like this, these CDFs don't necessarily have inverse functions because, or they don't have, they don't in general have inverse functions because, of course, a lot of values get associated the same function value by the CDF because there are these horizontal parts of CDFs of discrete random variables. So something close to the inverse of that is the so-called quantile function, which is defined as the smallest value of the random variable x. You can see here that there's still some x's in there, such that the probability for the random variable to take on values larger than x equals q. And the difference here, so if you go back to this definition, is here we can talk about p x equals q because we have an inverse function and we don't need to do this minimization over x, where in this generalization for the quantile function we look only at the px being larger or equal to q, and we need to do this minimization with respect to x. So we have a generalized inverse CDF here if you want. The good thing is that they exist for continuous and discrete distributions. If we have a continuous distribution, it just corresponds to the ICDF, so the inverse CDF. Right continuity ensures that this x actually exists, such that px is equal to or larger than q for all q in the open interval 0, 1. The value for 0 does not exist because the limit, if you go to infinity, is 0, so you would have to go to there is no real number essentially that this is fulfilled, because it only is happening in the limit that actually the CDF assumes the value 0, and the quantile function of 1 may or may not exist, because either the CDF approaches 1, then it does not exist, or it assumes the value 1 at one point and then it exists. So to exemplify this, here there's a figure from de Groot and Scherwisch, figure 3.6. Which kind of is a little test case to understand what's going on with the quantile function. So let's look at some examples. So if we assume that q is 1, then the smallest x such that the CDF of x is larger or equal to 1 is x4. So what you have to do to figure that out is, okay, you set a value here. So this is that's not the quantile function. This is just the CDF. So you start here. So you say q is 1. Okay. And then you go to the smallest value such that the CDF is larger or equal to 1. And because you're going from the right, you will always end up in a location that is actually defined, because you have right continuity, and you see that the smallest x for which the CDF takes on a value larger or equal to 1 is x4. And if you now think about Z3 here, the smallest value of x such that p of x is larger or equal to Z3, the smallest value is x3, and the same for x2 here. Now, if you consider an interval here z0 to z1, and you ask about what is the smallest x such that the CDF larger than q in this interval, you see that it's x1. Obviously it remains at z1 all the time, but the smallest x here is again x1. So this is kind of the beauty of quantile functions and the fact that they are that CDFs are right continuous. It's a little bit tedious. In principle, the easy way to remember this is that, okay, if we're dealing with continuous random variables, we have PDFs, they have CDFs. If we want to go from a probability to a value in the outcome space, we use the inverse CDF. Done. The thing is, if we are dealing with discrete random variables, we need to be a little bit more careful, and we cannot define these inverse functions because we have these big parts of identical probabilities associated with the parts in the real numbers. So what do we do? Well, we can invent the quantile function. So that's the reasoning here. Good. So that is what I wanted to do. Actually, there's a reversal in the thing here. So we first talked about what random variables are, and then we said, okay, we can define the distributions of random variables with probability mass and probability density functions. You need to know the definitions of those, and of course, once you know the definition of a probability mass and a probability density function, you can, all random variables that you encounter, all distributions you encounter, you can basically put into this scheme. And then we spent some time on talking about cumulative distribution functions, because they will be important when we talk about statistical inference, specifically with respect to confidence intervals and hypothesis testing. There they really are central, and if you didn't understand what a cumulative distribution function is, it's really hard to understand how statistical testing with its control of false positive rates, how that works, or how you form confidence intervals. It's really hard to understand if you're not fluent with the notion of a CDF. However, in general, we will define probability models or probabilistic models just by means of PMFs and PDFs. Good. Then later on in the exercises, we will see an example for constructing the probability distribution of a random variable by means of an underlying probability space. We will look a little bit more into properties of CDFs, and we will look at the fact that there are more than one definition essentially of CDFs, which are sometimes useful, sometimes not. And then we will look at some visualizations in the programming exercise. Good. My suggestion is, because this took a little bit longer, that we postpone questions to the lecture to the first part of the exercise session. So when we start the exercise session at 1 p.m., if you have questions now regarding the lecture, write them down and we will discuss them in the beginning of the exercise session, and then we go to the exercises, because I will now have to get ready for the next lecture. So please write your questions down and then ask them at the beginning of the exercise session, where I will allocate time for that. Okay, then if you want to join statistical methods, we'll start at 9:30. Today the topic is calculus. Otherwise, I see you again at 1 with your questions ready, and then we'll discuss them. So thank you and goodbye for the moment. The first one is it's essentially a little bit more facts about cumulative distribution functions. So one thing is, because the cumulative distribution function, its value reflects the probability that the random variable takes on a value smaller or equal to x. The question is, what do you, if you're interested in the probability that a random variable takes on a value larger than x, which is actually, if you do hypothesis tests and critical values and so on, that's always something you're interested in. How do you get that, and how do you relate it to the cumulative distribution function? There, the result is that the probability for a random variable to take a value larger than x is 1 minus the value of the CDF at x, for all x in the outcome space of x. That's one thing. The other thing is, if you want to know the probability that a random variable takes on a value in a given interval, how can you evaluate this? And this then is possible by means of subtracting from the value of the CDF at the upper interval boundary the value of the CDF at the lower boundary. And one can kind of justify these things, which are fairly intuitive, maybe, I don't know. Definitely this is fairly intuitive here. One can justify them based on the probability space model. So this is the first thing, so doing it kind of in theorem form. So let x denote a random variable with outcome space calligraphic x, and let p denote its cumulative distribution function. Then the probability that x is larger than small x equals 1 minus px for all x. How can we show this? Well, the events that x is larger than x and the event that x is smaller or equal to x are disjoint, because this is larger, strictly larger, and this is smaller or equal to, and refer to the omega and omega which are mapped by x omega to values larger than x or to values smaller or equal to small x. Of course, any because this is based on a real number, all together both sets form the entirety of omega. So the union of these events is the entire probability space, and then this fact just follows from the fact that p is a probability measure, hence the probability associated with omega is 1. And then by sigma additivity, when we look at the union of these two events, which make up the entire omega, we can separate this probability by means of sigma additivity, and then we just put the smaller or equal to x on the other side, and this is already the definition of the CDF, and then we get this result. So what this helps a little bit is to get into the mood, or into the pattern, or I don't know, of thinking about these probabilistic facts based on the underlying probability space. Are there questions regarding this exceedance probability part? Doesn't seem to be the case. Then the other thing with the interval probabilities, so let x denote a random variable with outcome space x, and p again its cumulative distribution function. Then the probability that the random variable x takes on a value larger than x1 and equal to or smaller than x2 corresponds to the difference of the CDF evaluated x2 minus the CDF evaluated x1. For all x1, x2, where x1 is strictly smaller than x2. Here again, based on considering the three events here. First, the event that x is smaller or equal to x1, then the event of interest here, namely that x is larger than x1 or equal or smaller than x2, and another event that x is smaller or equal to x2. Then these events have certain properties, namely first this event here, x smaller or equal to x1, is disjoint from the fact from the event that x is larger than x1. So this is how you read it. So x is larger than x1, and here x is smaller or equal to x1. So this is the empty set, and the event x1 is equal to or smaller than x1, together with the event that x is smaller than x2, because x2 is strictly larger than x1. Together they are the event that x is smaller or equal to x2. So this is the relation of these three events, and of course we have here the fact that things are disjoint and that this event is a union, so we can use this. So the union, the probability of this union is equal to the probability of this, because this is these are the same events. Then because these are disjoint events, we can separate them into the sum. This was actually the case earlier also, because these were disjoint events. That's why this works. Otherwise we would of course need to subtract the union, but again here we have a disjoint event, and then we can put the p x smaller or equal to x1 on the other side, and these are then just the definitions of the CDF. So we get that the probability of this event, so this interval probability, corresponds to the difference in the CDFs for x2 minus the CDF for x1. Questions regarding these interval probabilities? Another way to look at this, if you think about continuous random variables where the smaller or equal to or strict inequalities don't really matter, is of course that you get the probability for a continuous random variable to be in an interval x from x1 to x2, where x2 is larger than x1, by means of integration. And if you want to integrate the PDF, you of course need the antiderivative, and the antiderivative is the CDF. So for continuous random variables, and then you get from the fundamental theorem of calculus, you get the solution for the integral, namely that you need to subtract the antiderivative, thus, or equivalently or analogously, the CDF of the upper interval boundary. Jesus, I'm saying it wrong all morning. You need to subtract the CDF from the lower interval boundary from the CDF value of the upper CDF from the CDF at the upper interval boundary. So this is also the fundamental theorem of calculus if you're thinking about continuous random variables and interval probabilities. And there I think you would justify it very differently than this is done here. Good. So the last thing that I want to mention in terms of CDFs is the notion that what I introduce here, the right continuous version, is not the only version of CDFs that you might encounter. And so on the one hand, that's the version of the CDF that you see most definitely in the Anglo-American literature, as I think so Kolmogorov in these Russian writings from the 20th century, they always worked with the left continuous CDF, which we will see in a second. And then one of the reasons I took this in here is that there is a course in the data science program, although it's not really a course designed for the data science program, but it exists, and it's also not uninteresting. So I followed along a little bit what this course is doing last summer term on non-parametric statistics by Frank Konieczka at Charité. And because we are doing here essentially only parametric statistics, I think it's for data science students, it might be interesting to also look into this non-parametric statistics course, because that's also a big part of statistics, of course. And they are dealing with what is known as or what they call, or what Brunner, I think, who was the PhD supervisor of this Frank Konieczka guy, calls the normalized version of the cumulative distribution function. And when I first encountered that, I was confused, because I thought I knew a little bit about probability theory, and this didn't come across, but I hadn't seen this before. And so I felt a little bit, well, I should have prepared the data science students for that. So this is what I'm doing now. The thing is, it's fairly idiosyncratic. So I also Googled again around when I prepared this regarding the normalized version it seems fairly specific to these Brunner people and their non-parametric statistics, although there it's actually quite important. So the idea is to briefly discuss the right continuous, left continuous, and the normalized version of the CDF. So what we've seen here, which are called large P and will call large P all the time, is the right continuous version of the CDF. So it's defined as the probability that the random variable takes on a value smaller or equal to x, and that it's right continuous. We showed with a little bit of the help of a miracle, because it's fairly deep, and this exchange of the limits, or taking basically this infinite union and then taking a limit out, that's one could of course analytically justify much more than we did, because we didn't justify it at all. But we learned now that this is right continuous. And we also looked at this example when we looked at the quantile function. One can also define the CDF, and you sometimes see that, and it makes sense to pay a little bit attention when people introduce their CDFs, whether they actually write smaller or equal than or smaller than. If they write smaller than, they use the left continuous version of the CDF. Now, to show that this is left continuous, so that it's continuous if you approach limit points from the left, so from minus infinity, and not from the right, so from plus infinity, is again work, and I had brief search around it, but then I decided we omit this because it's I mean, we didn't do the right continuous properly, so why fiddle with that? For what I'm mostly interested in, namely continuous random variables in parametric statistics, because they're continuous, it doesn't matter anyway, because they are the same for all x in the real numbers. But for discrete random variables at points where the discrete random variables assumes non-zero probability, the right continuous version is always strictly larger than the left continuous version, and actually the probability for a discrete random variable to assume such a value x0 is just given by the difference between the between the right and the left continuous version. And this can create a problem if you want to assign a CDF value to a specific value x0, and you actually have if you want to create a CDF, and you have the case that that you have two different CDFs, and so the compromise here is to take actually as the value for the CDF at axis where this occurs, that you take the average of both versions. So why this is really useful, you have to ask Konieczka. There I didn't go that deep into the non-parametric statistics where this really helps, but I can at least show you a picture and try to make this intuitive. So what we are dealing with is the one here in the middle, which is right continuous. So if we're here at x, down here, then we allocated to it the cumulative distribution function here, where the dark dot is. If we would use the left continuous version, so if we talk about the probability for being smaller than x, then we would allocate to each x the value that is here corresponding to this dot, because that's the limit point, and the continuity comes from the left and not from the right. So here we have from the left we have this jump, and the definition for the value of the CDF at the location X where there's this jump is this value up here because we are continuous from the right. Here it's down here because we're coming from the left. And then of course this can make quite a big difference in terms of what you now call the CDF value for some value X. And then the idea of these Brunner guys, based on some obscure papers from the 80s, is to use neither this larger CDF value corresponding to the right continuous version, nor the smaller value corresponding to the left continuous version, but the average. And yeah, essentially I wanted to tell you that something more than we are doing here exists, and that in your data science studies you might encounter that. But please press Frank Konieczka to explain why this is essential, because when I followed his course, I mean, I didn't really take part in the course, I just via other students I saw what they are covering. I think it didn't quite get clear why this is so essential. So please press him to explain that if you really want to know. But yeah, now you know that something like this may come up. Good. Questions regarding these other CDFs? Okay, that doesn't seem to be the case. Then we can already go to our programming exercises, and I am not completely clear who's doing what, but you will tell me. So the programming exercise specifically with respect to the random variable simulations and histograms visualizations, they are quite straightforward. I mean, we did something very similar in the first week, but I think it's also, after all this theoretical overhead in terms of what is a random variable, what is a probability mass function, what is a PDF, to ground this a little bit or to yeah, to emphasize the real practical or the more important aspect of the theory, rather than whether something is left continuous or right continuous, which can also be very practical implications, but it's also more subtle math. Thing is, if you simulate a Gaussian random variable with expectation parameter around 3, the values that you see most of the time are values around 3, and this is also important. So this is where these exercises are heading. So who's